difference between force problems and torque problems is that when we drew out information about force problems, one of the first things we asked ourselves was, is the object accelerating or not? Do you guys remember that question? Now we're going to ask that same question, but there's two different kinds of acceleration now. There's changing location. That's a translational acceleration. That word translational is going to get used a lot. And then there's rotational acceleration, or an angular acceleration. So those correspond to translational values for force and rotational values for torque. Now for the time being, we're going to talk about problems that are in static equilibrium. Objects that are in static equilibrium are not accelerating, which means the net force equals 0 and the net torque equals 0. So like our bridge. Our bridge has two supports, and it has to support its own weight, but we want bridges to stay where they are. We don't want them to accelerate. So the whole idea is that you design a bridge so that regardless of the stressors on the bridge, it remains in static equilibrium. So I want to start by thinking about how we would have done this problem, say back in October when we first started talking about forces. So we know the meter stick has a weight of 0.69 newtons. And there's T1 and T2. We know that those are splitting the weight up almost evenly because we have that on the screen behind us. And we kind of set this up, so I want to kind of reiterate this. This is at the 20 centimeter mark. The meter stick is pretty uniform, so its mass is at the center, so 50 centimeter mark. And T2 is at the 80 centimeter mark. But let's say I grab the 500 gram mass. The 500 gram mass is 0.5 kilograms, and it has a weight of 5 newtons, because 0.5 times 10 is 5 newtons. And let's say we put it, I don't know, let's pick a spot. How about at the 70 mark? Is that good for you guys? So 5 newtons here at the 70 centimeter mark. If I wanted to figure out how much stress is being applied to both supports, I would probably start this problem like we started the old style problems from the beginning of the year with net force equals 0. I can identify all the forces acting in the system. I could draw a free body diagram if I wanted to identify those forces as they act in the system. But I think we could all agree we'd get T1 upwards plus T2 upwards minus 0.69 downwards minus 5 downwards, and that would all equal 0. What should be painfully clear is that there's no way with this information alone for us to figure out how much each support has to support the weight. There's nothing here about where the support is. We just know together the two supports have to support the weight. Now, this problem can't be solved with force alone. This problem has to also use torque in order to solve it. And a net torque problem is very similar to a net force problem. In fact, if you remember the steps for a net force problem, you're going to do almost all the same things, but there are small differences. So I'm going to go through the set of steps that you have to do to solve a net torque equals 0 problem. This is specific to static problems. It will not be true for dynamic problems, only for static problems, because there's some things we can do here that only work with static problems. And so I'm going to go through a set of steps. I'm going to say each step out loud. I'm not going to write it down. I'm just going to say each step out loud, and then we'll apply the steps one at a time. Ready to go? One major difference between a torque problem and a force problem is that where the force is applied matters. So you noticed I didn't draw a free body diagram this time. I I drew the object as it looks and drew the forces at their point of application. So our free body diagram is going to change. It's now going to be the shape of the object experiencing the forces. So step 1, draw a simple sketch of the object. Step 2, draw each individual force at the point of application of the force. Draw each individual force at the point of application of the force. So again, the disclaimer here is for a statics problem, meaning your problem is at rest. If that's true, then for step 3, you can choose anywhere to be your pivot point. You can choose anywhere to be your pivot point. Step 3 is actually pretty simple. If the object's not rotating, then there is no defined pivot point, but torque requires a pivot point in order to calculate it. Again, because the system's not rotating, there is no predefined pivot point, but torque requires a pivot point in order to calculate it. So you must choose a location for your pivot point. You must choose a location for your pivot point. Here's the best part about it. If you'll recall, the pivot point, we draw a little triangle as our pivot point, just as a way to indicate it on our diagram where the pivot is or where the fulcrum is. You can place it anywhere you want. But think of this part. The pivot point determines where all of the torque arms will be measured. So wherever you place the pivot point, you'll be measuring the torque arms from that location. For example, I could put it all the way here at the end, which would be a reasonable place since I know all the distances already. Right? I know the 20 and I know the 50, the 70, and the 80. However, if you'll remember, the definition of torque says torque equals torque arm times force times the sine of the angle. If you're pretty shrewd, and I know a few of you in this class are very insightful, you'll realize that you could put it someplace useful to you. For example, think of it this way. If I place it here, what is the distance from the pivot point to T1? What does that do to that torque? It cancels it out. It means that torque would be 0 based on this pivot point. So you can place the pivot point anywhere you want. I would encourage you in problems like this to place the pivot point at the location of an unknown value of force. It will reduce the number of unknowns. It will make the math easier. You can place it anywhere, but some places are better than others. So again, you can place the pivot point anywhere you want, but I would place it at the location of an unknown value of force, because it will cancel out that torque. Remember first semester when we could choose our coordinate system to be any one we wanted, but if we lined it up better, we can make our problem easier? This is similar. This is helping to line up our problem to make it easier. Once we have chosen a pivot point, the rest of our problem is very much like what we did for force. We're going to add up our torques and set them equal to 0. So what I suggest you do is get an idea for the torques that are in your problem. I see 3. Right? I see 3 different forces that are acting some distance away from the pivot point. Do you see that? So what I recommend you do in step 4 is make a chart of all of your torques. Again, you can do this however you want, but I think for step 4, make a chart of all of your torques. This is what I would encourage. We know that this is the structure of a torque. So my chart's going to have the torque from the weight of the meter stick and the torque from my 5 Newton mass and the torque from tension 2. I know I'll have 3 torques. And I know that these torques are going to sum up to be equal to 0. And each torque is going to have 3 things. All right, I'm setting up a chart. It's just a way to help remind me that there are 3 things I have to consider for each torque. But I'm going to add them up to equal 0. Does this make sense so far? Well, I need to fill in my chart, so I think that's part of step 4 is filling it in too. So I set up the chart, then fill it in. So I'm going to go to each one of my torques and we'll evaluate it. So let's talk about the weight. The first thing is the torque arm. So when I look at these parts of a torque, the first part is the torque arm. That's the distance from the pivot point to where the force is applied. So for our first one, I'm starting at 20 centimeters and pointing to 50 centimeters. That's my first torque arm. Well, what's that distance? 30, but I should put it in meters. So I'm going to put 0.3. Next, I put in the size of the force. We know the weight of the meter stick was 0.69 newtons. Last, I have to figure out the angle between the torque arm and the force, but my bridge is horizontal and the force is downward, so I think we're looking at 90 degrees. Does that make sense? Let's move on to the next torque. So my next torque, well, that's going to be from, all right, it's going to be from my torque arm all the way to here. That's from 20 to 70. How far is that? So 0.5. Size of the force. That's what we're going to hang, 5 newtons. Can you also agree that that's still going to be 90 degrees? All right, last one. We're going to go from 20 to 80. So 0.6. We don't know the size of this one. This is going to be our unknown, so I'm just going to put in T2 because we don't know what the size of that one is. Does that make sense? And then can we agree that this is also 90 degrees? Now step 5 is going to be tough for some of you because this is where we have to use the right-hand rule or we have to use clockwise and counterclockwise. But step 5, we have to assign positivity and negativity to each of our torques. So I think for this class, and in the interest of time, we'll just use clockwise and counterclockwise. Is that okay with you guys? So the first torque is from the weight, and it's trying to get my meter stick to go this way. Would you agree that that's clockwise? So do you guys want clockwise to be positive or clockwise to be negative? All right, so if clockwise is positive, then we're going to say that this particular torque is positive. Can we also kind of see that this weight that we're hanging is going to also be a clockwise torque, and therefore it's positive? Right, because it's trying to get it to go in that same direction. So I'll put positive here. But T2 is trying to pull it in the other direction. Do you guys see that as well? So that's going to make that one negative. Tomorrow when we do this, we'll use the right-hand rule to show how it's the same thing. But good so far? Or do you want to do the right-hand rule now? We can do the right-hand rule now. It's easy. That's literally it. Once we're done, you should be left with something that you can solve for your unknown. It's going to generate a relationship the same way any of these force equations generated a relationship. Had we not put the pivot point at one of our unknowns, it would have generated a relationship with multiple unknowns. But by putting the pivot point at a location of an unknown, it just generated a relationship that has only one unknown in it. But now we have to do some math, so we got the calculator thing going on here. So 0.3 times 0.69, that equals positive 0.207 plus 0.5 times 5 is 2.5 minus 0.6 T2 equals 0. So this is step 6. Add up all your torques and generate a relationship. We have actually two relationships. We have this one, and we have the one that we generated at the beginning. So there's two relationships here. One from net force and one from net torque. But it looks to me like we could solve the net torque one for T2. So let's do that real quick. I'll get 0.6 T2 equals 2.707. So T2 equals 2.707 divided by 0.6. I get 4.51 newtons. Now, since I already have another relationship here, I can figure out what T1 is because I know they both have to add up to be 5.69. So 5.69 minus 4.51, and I get 1.18. So now let's check it out. Let's see if it works. To do that, I got to put my weight at the 70 centimeter mark and make sure that my other strings are 20 and 80. So 20, 80, 70. All right, let's see. All right, so I got 4.41 and 1.15. I'd say pretty darn close, wouldn't you? I did notice that as we were going on, it looked like that the weight at the end was a little bit less in the beginning. These things do slowly get out of calibration as they sit here. But not bad. Not bad at all. Now, something to keep in mind. There are places that don't work.